Hey everybody, I'm Thomas. Today we're going to talk about Dapp Architecture on CKB using the Lumos framework. So this is part 4 in the CKB Workshop series. In previous episodes, we've introduced the concepts of CKB, including cells, scripts, and transactions. We've explored script development using Capsule and transaction generation with Lumos. If you haven't seen the previous videos in the series, I recommend you check those out first if you're not deeply familiar with the subject matter. Today we'll learn how to leverage the Lumos framework to build decentralized applications, by firstly going over their architecture and then seeing that in practice by walking through the code of Hello Lumos, a Dapp template that's designed to serve as a starting point for your own apps. In a follow-up video, we'll use this understanding to integrate the NFT functionality from the previous workshop demos into this full application. So a brief note on prerequisites. In addition to the material in the previous videos, you should have a general familiarity with Web 2 client-server apps. The starter Dapp is written in JavaScript and TypeScript on both the client and the server. The client also uses the React framework, so at least some familiarity with these technologies will be quite useful. However, if this isn't your stack of choice, there should still be plenty to learn from both the structure of the application and from the examples of how to interact with CKB programmatically. So with that said, let's get into how to design dApps on Lumos. If you recall in the previous workshop, we went over the various components of Lumos and showed how they work together. Firstly, a connection with a CKB node is established, and the Lumos indexer indexes cells locally. These cells are then used to generate transactions or to respond to other queries involving the cells. Today, we'll essentially be expanding upon the user interaction part of this diagram, showing how we can integrate Lumos into the context of a full application to leverage its power. dApps on Lumos are architected around a familiar client-server model. There are essentially 3 components: the client, the server, and the wallet. The server handles interactions with the CKB network, doing blockchain-related tasks like querying data and generating transactions with Lumos. It provides a user-friendly REST API for the client, abstracting away the details of this blockchain interaction. The client component is the user-facing app, displaying the content and responding to user actions. The wallet is the final component and is used to sign transaction requests for the user. Although it is of course user-facing as well, it's logically separated from the rest of the client app. This is both for the security of user private keys and to facilitate dApps interacting with the many wallets in the ecosystem. The Hello Lumos example app comes with support for Keypering, a desktop wallet for Dapp development, by default. If you want to learn more about Keypering and external wallets, I'll provide some links down in the description. So let's dig a little more into the server component. As mentioned, it's essentially a wrapper around Lumos functionality. It uses the Lumos indexer to maintain a database of cells, and then uses these to respond to user queries and transaction generation requests, which are represented over a higher level REST API. It also serves as a simple intermediary for common interactions with CKB nodes that a client might want to do, such as fetching the latest block or status of a transaction, such that client apps can use a more familiar REST API and not have to manage their own connections to the node. So let's look into the example of finding a CKB balance for a given address. The client queries a getBalance endpoint on the server for the given user. In order to calculate this balance, the server uses its index database of cells to find all the simple CKB cells owned by the given user. It sums their capacities to come up with an overall balance and then returns just this balance to the user, abstracting away this detail. So the flow for conducting transactions is generally a bit more complicated than a query. Let's say the user wants to transfer CKB. First, the user expresses this action as a high-level intent, such as transfer 1,000 CKB from A to B. And then we need to convert this to CKB language on the server. The server builds a Lumos transaction skeleton, represented by this little dinosaur here. This structure contains all the cells and dependencies for the action, though it lacks the witness signatures required to make it valid. However, the skeleton includes the data that needs to be signed. After the client gets the skeleton, it forwards it to the wallet for signing. While we really only need to send the signing entries piece of the skeleton, which contains the actual data to sign, we go ahead and send the entire structure, as well as the intent of the transaction, to the wallet. This helps show the transaction to the user in a user-friendly way. The wallet is of course free to do its own analysis of the transaction, but this is left to the discretion of the wallet. Assuming user approval, the wallet returns the required signatures to the client. The transaction with signatures is then forwarded to the server, where it is sealed by adding the transaction signatures to the transaction structure. The complete transaction is then forwarded to the node, and upon successful receipt, the node returns the transaction hash, which can then be sent back to the client such that it can track the transactions on the user's behalf. So we can think of this flow as having 4 steps: build, sign, send, and track. Going back to the more detailed view, we can see how these actions map to the build step, the sign step, the send step, and the track step. Due to this flow, on the server we separate the logic around a given transaction type into 2 endpoints, one to build the initial skeleton and one to send the finalized transaction. I wanted to add a quick note that this flow isn't set in stone. Many wallets, including Keypering, are perfectly capable of sending transactions themselves, so we could avoid passing the signatures back to the server via the client. However, it makes sense for the server to retain this functionality because some wallets might not support this, and we're guaranteed that the server has a connection to the node. Next up, let's get into the code walkthrough of the Hello Lumos app and see how this architecture looks in practice. So for the Hello Lumos example app, we'll need to set up a local node and wallet. Let's start by running a CKB node connected to the Agron 4 testnet. I already have CKB installed and configured, so I'll just run that by using CKB run here. If you haven't configured a local testnet node yet, the instructions for how to do so are at the main Nervos doc site. Next, we'll need a Keypering instance running, with some testnet funds in the wallet. I have the latest source downloaded, so I'll go to the Keypering repo and run npm start. The instructions to build or install Keypering are here at the Keypering repo. There are instructions to build from source with the commands here, or to alternatively install for your platform via the latest release. In order to get Keypering connected to testnet, you go to the settings menu and set the network. If you need capacity for testnet, check out the faucet, where you can paste your address here and claim CKB. Once that transaction is processed on-chain, that capacity will appear in your wallet. So now that the node and wallet are set up, let's clone a fresh copy of the Hello Lumos repo. Looking at the files, you'll see that the repo is divided into 2 main sections, the client and the server. Because we're using Yarn workspaces, Yarn will handle the dependency installation for both sections by just running it in the base directory. So I'll give this a minute to install and be right back. Now that our dependencies are ready, let's take a look at the server code. It's a pretty straightforward Express server that converts API requests from the client into blockchain queries and transactions using Lumos. In the index file, after our imports, we'll configure our environment. We take a couple environment variables from the env file and then initialize our Lumos config. We're using the default Lumos config for the Agron 4 testnet, so we don't have to do anything else to set this up. The environment file specifies ports, URLs, and directories used by the server. You won't need to change this, but are welcome to if you want to configure things differently. Next up, we initialize our connections to the node. So we set up an RPC connection to the CKB node defined in the env for handling standard RPC calls. Then we set up a Lumos indexer with a connection to the same node to maintain a local database of cells for efficient transaction generation. Then we set up some Express middleware for parsing JSON input and for accepting cross-site requests from our local client. Next up is the core of the application, the API routes. If you're not familiar with this syntax, this allows us to bundle our routes into files and include them at different base resources. So these general routes are located at the base resource, indexer routes use the indexer prefix, and CKB routes use the CKB prefix. I'll go into these routes in more detail in a second, but firstly, to complete our setup, we start our indexer and just announce that our server is running. So let's go check out the routes in more detail. Going into the routes folder, we'll start with the general routes. These are essentially wrappers around some common RPC calls that the client would want to make to the node. One of these would be fetching the latest block. You can see that we just fetched the latest block via the RPC connection and return it in a JSON format. There is also some basic error handling to forward errors to the client. Next up is an endpoint to fetch transaction statuses. We receive a list of transaction hashes, query the node for the status of each transaction, and return this to the user. We have a little helper method here that gets each transaction by hash from the node and extracts the status. Looking at the CKB getTransaction RPC call, we can see that we'll get back the full transaction structure, as well as a status and the hash of the block where the transaction has made it onto the chain, if any. So with the statuses, there are three possibilities: pending, proposed, and committed. A pending result means the node is aware of the transaction. A proposed result means the node sees a transaction included in a block candidate that is not yet mined. And a committed result means that the block involving the transaction has been mined and is officially on-chain. Going back to our endpoint, we're going to gather these statuses and return them in a JSON format to the client. So moving on to the indexer routes, there's a single route, getCells, which is a simple wrapper around the cell collection process. In our example app, the client isn't interested in cells directly, but if they were, they could query this endpoint with the same parameters used normally to query index cells in Lumos. The CKB routes are the core substance of the application for our example app. The first endpoint is to get the balance of an account by lock script. To do this, we use a generator defined in the generators folder. You can see we find all the simple CKB cells for our user, sum their capacity, and then return this as a balance. So there are two routes for transferring CKB that you'll recognize from the earlier section. First, we have a route to build a transaction skeleton for a transfer, taking in the parameters specified by the user. The user expresses their desired action in a higher level format as shown here, with a sender, recipient, amount, and fee. The server then uses a generator to build this from the current set of live cells. CKB transfer generators are actually already included in Lumos as they are a common function, so our generator here is just a little wrapper around existing functionality. So here we can see the composability possible when building transaction skeletons. So first we create a transaction skeleton, we add the transfer operation to it, Lumos will find the appropriate cells here and compose them to express the intent of the transfer. Next up, we add a fee to the transaction. In our case, the fee payer is the same as the sender, so Lumos will intelligently minimize cell usage, taking into consideration the skeleton constructed by the previous transfer generator. Note that it's also possible to have someone other than the sender pay the fee, which is a nice demonstration of the flexible composability. Next up, we prepare the signing entries. These are the data that the user's wallet will need to sign to provide valid witnesses for the input lock scripts. And ultimately, we forward the structure to the client. The final endpoint is the one for sending a signed transfer operation to the chain. Note that we actually don't take the skeleton back as a parameter here, but rather the original intent, because we can derive the same transaction skeleton from that. We rebuild the skeleton using the same process as before, seal the transaction with the required signatures, and send this finalized transaction to the network. If the transaction is accepted, we'll return the transaction hash to the user for tracking. We'll also forward all failures to the client, which can interpret and display these in a user-friendly way. So that's about it for the server. It's pretty straightforward thanks to Lumos taking care of most of the heavy lifting for us. The client is a pretty standard React app based on the Create React App TypeScript template. Because we've just been looking at the API routes, let's see how the client interacts with the server and other external components. The services handle these external connections. The Dapp service is for the connection to our server. It essentially provides TypeScript-friendly wrappers around the API calls, parsing return data and handling errors. You'll see the various endpoints from the server represented here. There is also a wallet service that manages connections to wallets. Here we provide a wrapper around our interactions with Keypering for now. So looking in the wallet service, we can see that one of the functions is for getting a list of accounts. It's worth briefly mentioning how accounts are stored. We maintain a record of each account by lock script, lock hash, address, and public key. Because accounts can be represented by each of these values in different contexts, we keep all this data on hand. Back in the wallet service, we have a method for requesting authorization from the wallet in order to connect to it. For Keypering, the client needs to get this approval initially to interact with the wallet. Here we also have a method to request signatures for a transaction. The specifics of Keypering's RPC methods are covered in its documentation. Digging into the component hierarchy, the first thing of interest are the stores. These are used for application-level state management and leverage React hooks for a Redux-like functionality. This allows any component in the hierarchy to use and modify information in the stores, rather than managing data dependencies using props, which can get messy quickly. Let's check out one of these stores to get the gist of what's going on. The balance store maintains a cache of the CKB balances of various accounts that we're interested in. As you can see, the state consists of a map of lock hashes to balances, which are stored using the big int format. It's important not to store balances in normal JavaScript numbers, as they can lose precision at the high values required to express CKB and token balances. The reducer here contains all the functions to modify the state in this store. As you can see, all we do here is set the CKB balance for a given account. This reducer action is mapped to a local function which simply modifies the state object appropriately. Because we're leveraging the useReducer and useContext hooks, we can use the state and dispatch functions anywhere in the app. The components that use the state are automatically re-rendered when it's changed. There are a few other stores here that follow a similar pattern. The modal store maintains app-level state regarding the display of modals. The transaction tracker store keeps track of transactions that we've made through the UI such that the user is aware of the status of their actions. You'll recognize the transaction statuses here that we discussed earlier in the enum. We also keep track of the latest block number that we fetch data for to know whether we should refetch the transaction statuses in response to a new block. Finally, we have the wallet store that maintains local state regarding the accounts from our connected wallet. Just below the stores in the hierarchy, the data manager is a key utility component that handles fetching data from the server. You can see here how it uses the state and dispatchers. It has a few key functions. If the active account changes, we go ahead and fetch the CKB balance of that account. We get the active account via the connection to our wallet. We also poll for new blocks from the server every second so that we can be alerted when new blocks arrive. This is useful for tracking the status of the user's transactions. If we see a new block, we update the latest block and then go ahead and check the status of each pending transaction. We also go ahead and refresh the CKB balance for the active account if there is one. While some sort of pub subsystem would be more efficient here, this is the simplest solution to be responsive to the blockchain state. Let's go ahead and start the client so that we can see it live. I'll run yarn start in both the client and server directories to start them both up. Going over to the UI, let's log in using Keypering. The request auth function of the wallet service is triggered on click here, asking Keypering to approve interaction with our app. Once authorized, we fetch the accounts and keep these in our local state. Note that because our active account was changed, we'll automatically fetch the balance for this account. Next up, let's transfer some CKB. We can enter some values in the form, and now Keypering pops up again, and we can see the signature request in our wallet. Keypering gives us an overview of the details, in which we can clearly see the transfer that we intended. Approving the transaction, the signature is returned to the server and we end up with a transaction hash to track the status, which is displayed in our table. Now let's go to the transfer CKB form component where this happens and see the build, sign, send, track flow taking place. This form is built using the React Hook Forms library, which is a nice library by the way, but we're ultimately interested in what happens when we submit the form. To reiterate, we ask the server to generate a transaction skeleton representing the high-level intent. This happens under the hood. Notice that we didn't see any indication of server activity going on when we submitted the form. Once that skeleton is returned, we forward it to the wallet. Note that we have some conversion logic here, as Keypering takes in a slightly different transaction format than Lumos generates. We then take the signature, send the complete transaction, and track the hash. So that's about it for the overview of the client. Hopefully this workshop on building dApps using Lumos and the starter app repo are useful to you as you dream up your own CKB applications. Thanks for tuning in. If you'd like to get more information or have questions, you can check out the Nervos docs and come join us on Discord and Telegram. Also, feel free to reach out to me personally at the handle shown on either of those platforms.